a humanoid robot watched a video on a smartphone, and then it danced. Not just any dance. It reproduced the REDRED challenge by K-pop group CORTIS, one of the biggest viral phenomena of 2026, with arm movements, synchrony, and rhythm. No motion capture studio, no team of engineers manually programming every gesture. Just a smartphone, an open algorithm, and a South Korean company called ROBOTIS. What looks like magic is, in reality, something more unsettling. It's a sign that teaching complex movements to a robot may be on the verge of becoming as easy as filming a TikTok. Want to understand everything? Then watch the video to the end, and I'll explain it all. But first, subscribe to the channel to stay informed about the latest developments in robotics. There is a scene that has been etched into the memory of many people who work with robotics. It's the scene of an engineer spending hours, sometimes days, manually programming the movements of a robotic arm so it can pick up a simple object from the floor. Every millimeter of trajectory, every joint angle, inserted line by line into the code. And in the end, sometimes the robot still stumbles. Now imagine a completely different scene. A researcher picks up a smartphone, films a person dancing with those fast crossed arm movements and the hand waving near the ears that took over TikTok in 2026, and uses that video as input for an artificial intelligence system. A few steps later, a humanoid robot is reproducing the choreography with coordination, balance, and precise timing. The company that did this is Robotics, with the K0. The robot launched a few months ago as open source. The K0 is powered by DynamicXL-Q actuators, Robotics' own newest generation of technology, developed specifically for humanoid robots. There are 23 units in total, of 2 different models. What sets them apart from common motors is QDD technology, quasi-direct drive, which combines high-torque motors with low gear reduction. In practice, this means the robot can respond to external forces naturally, without locking up, and precisely control the intensity of each movement. It's like the difference between an arm that pushes with brute force and a hand that holds a glass with calculated delicacy. The brain of the K0 is an NVIDIA Jetson Orin NX processor with 16 GB of memory and processing capacity of up to 100 TOPS, 100 trillion operations per second, the performance measure for embedded artificial intelligence systems. For comparison, it's the same type of chip that equips autonomous cars and advanced military drones. It fits inside a robot you could place on the backseat of a car. The battery is 46.8 volts and 9,000 mAh. And the entire platform, including mechanical design files, software code, and simulation assets, will be made available as open source for researchers, developers, and students around the world. The dance itself, nicknamed Flappy Ear Dance by fans, with movements that cross the arms and wave the hands near the ears, was designed to be simple enough for anyone to copy, which made it perfect for viral challenges. That's exactly why Robotics chose it. Not just as a curiosity, as a proof of concept. What the team wanted to demonstrate was that AI Sapiens can learn complex full-body movements with arm coordination, balance, synchrony from a video recorded on any smartphone. Without professional motion capture equipment, just the video, the learning system, and the robot. Let's start with what seems to be the simplest detail: a smartphone video as a starting point. It's almost banal for how everyday it is. But this detail is, in reality, the entire revolution wrapped in a gesture that any one of us makes every day. Think about it this way. Teaching movements to a robot, until not long ago, was like trying to assemble a 1,000-piece puzzle using only words. You had to describe every position, every angle, every moment in time, in a way that the computer could understand. This was called trajectory programming, and it required specialized engineers, weeks of work, and, in the case of complex movements like dances, professional motion capture studios. These studios, the famous mocap studios, are spaces filled with infrared cameras, with actors wearing suits covered in reflective markers all over their bodies. The software tracks each marker in real time and converts the movement into digital data. It's the same technology used in Hollywood films, video games, and scientific simulations. And the price? Professional studios charge between $1,500 and $3,000 per day of capture. Complete industrial-level equipment costs between $25,000 and over $100,000. Hiring a certified technician for maintenance can cost between $1,200 and $2,500 per year. Robotics eliminated all of that. With a smartphone, the process begins with video-based motion capture, which is exactly what the name says. The system analyzes the images from the video and automatically extracts the position and movement data of the human body visible in the recording. That's the first step, and it's already impressive on its own. The second step is what the team calls motion retargeting, which is the translation of that human movement into the robot's body. Think of it this way. You and the K0 have completely different bodies. Your arms have one length, the robot has another. Your knees work one way, the K0's knees work another way. There is a physical limit to how much each joint can rotate. Retargeting is the process of adapting the captured movements to the real physical proportions and limitations of the K0, without losing the essence of the choreography. Up to this point, we have data. The system knows what the K0 should do to reproduce the dance. But knowing is not the same as being able to do it. And this is where the most sophisticated part of the entire process comes in. The third step is reinforcement learning in a simulation environment. Think of reinforcement learning as a very accelerated trial and error game. The robot, actually a digital version of it inside a simulator, tries to execute the movement. It falls. It tries again. It adjusts its balance. It falls again. With each attempt, the system receives a score. The more similar to the original choreography, the more stable the balance, the better the score. And the robot learns, on its own, which adjustments make its score higher. Robotics uses NVIDIA Isaac Sim for this, a highly precise physics simulation environment developed by NVIDIA that replicates the laws of physics with enough fidelity that the behavior of the virtual robot is very similar to what would happen with the physical robot. In simulation, this trial and error process can happen thousands of times in minutes, something that would be impossible with the real robot, because every physical fall causes wear, can damage parts, and consumes time. And here is the fourth and final step, the sim to real transfer, from simulation to reality. After the AI Sapiens learn to execute the choreography in the virtual world, that learning is transferred to the physical robot. The Dynamics LQ motors, with their low impedance characteristic and precise torque control, are fundamental here. They allow the robot to execute the movements learned in simulation with much less friction between the digital and the physical, reducing the gap between what the robot does in simulation and what it manages to do in the real world. Robotics plans to release this entire pipeline, from video to dance, as open-source software. Any researcher, developer, student, or curious person will be able to download, modify, and use the same tools that produce the robotic dance. The K0 has 23 degrees of freedom distributed throughout the body, 5 in each arm, 6 in each leg, and 1 at the waist. In practice, this means it can perform full-body coordinated movements, tilting the torso, rotating the hips, raising and crossing the arms simultaneously. This is what makes possible a choreography that requires synchrony between the upper and lower body. For reference, typical industrial factory robots have between 4 and 6 degrees of freedom. The K0 has nearly 4 times more. The load capacity of the arms is 3 kilos per arm, the equivalent of carrying 2 1.5 kilo bags of rice at the same time, 1 in each hand. It's not much compared to large industrial robots, but it's suitable for everyday tasks, holding tools, manipulating household objects, carrying trays. But what can the K0 not yet do? The robot is in active development. Bipedal locomotion, walking, maintaining balance on uneven terrain, climbing steps, is still being refined based on reinforcement learning in NVIDIA Isaac Sim. Public videos show the K0 walking on flat, controlled surfaces, but there are still no demonstrations in challenging outdoor environments with unexpected obstacles or uneven surfaces. The Dynamics LQ actuators themselves have not yet reached the general market. Robotics foresees their commercial launch for the second half of 2026, and this timeline may change. Without the actuators publicly available, independent researchers still cannot assemble the K0 on their own, even with the design files being open. The robot's field of view depends on embedded cameras and sensors, but Robotics has not publicly detailed the specifications of the perception sensors, such as depth range, ability to operate in low-light environments, or detection of moving obstacles. These are technical questions that the research community will explore as the open-source code is progressively released. And the battery? With 46.8 volts and 9,000 mAh, the K0 has a reasonable energy reserve for a robot of its size. But the real autonomy and continuous operation of intense movement, like a complete choreography repeated several times, has not yet been publicly disclosed. What robotics experts immediately notice in Robotics' approach is the choice of open source at a time when most companies are going in the opposite direction. Tesla, Unitree, Agility Robotic all develop their robots as closed platforms with proprietary code and exclusive hardware. Robotics is betting that openness generates more collective innovation than secrecy generates competitive advantage. It's a philosophical bet with historical precedents. It's what happened with Linux in operating systems and with Android in smartphones. The question is whether the same model works for complex physical hardware, where opening the code doesn't necessarily solve the problem of manufacturing and accessing quality parts. In terms of direct comparison, the AI Sapiens K0 competes in a specific segment. Research humanoid robots below $10,000. The Unitree G1 from Chinese company Unitree Robotics is its closest rival. Also focused on agility, also aimed at researchers, also with advanced bipedal locomotion capability. The G1 excels in locomotion speed and robustness on varied terrain. The K0 bets on the accessibility of the learning pipeline and the open-source philosophy. These are different emphases for partially different communities. In a broader context, the K0 also inserts itself into the ecosystem of the K-Humanoid Alliance. The South Korean government alliance launched in April 2025 with a planned investment of $770 million through 2030, bringing together more than 40 companies and universities with the goal of making South Korea a global superpower in humanoid robotics. The most immediate ethical question is not about jobs, it's about data. If robots learn from videos made by ordinary people, who owns the captured human movement? If a TikTok video of an amateur dancer trains an industrial robot, does the dancer have any rights over that use? These questions still have no clear legal answer in almost any country, and the speed at which the field is advancing suggests that regulations will come after the fact, not before. What is your opinion on this? Do you think robots can reproduce choreographies, artworks, and other human creations? Leave your answer in the comments. If you liked the video, leave a like and subscribe to the channel. That way you will always receive notifications of new videos. See you next time.